My name is Michelangelo D'Agostino. I lead the data science team at Civis Analytics. This is Bill Latner. He's one of our awesome senior data scientists. And we're excited to tell you a little bit about the power of persuasion modeling. So persuasion modeling is a kind of predictive analytics technique that we think is super interesting, really powerful, but on the flip side, not all that kind of discussed or appreciated in kind of the data science and machine learning community. So we're excited to kind of introduce the topic to you. And the goal for the talk is really just to give you an introduction to the problem, some of the basics of the methodology and the techniques, and then walk through a bunch of case studies, but so that you can kind of walk out of here with a really clear idea of when you might want to use a technique like this in your own work, and then understand kind of the basics and the terminology so that you could then go to the literature, use some familiar packages, and then implement it in your own work. Before I go on, I should say I've been really sick this week. Today's actually the first day I have my voice back. So if my voice goes out or I just collapse on stage, Bill's going to roll me off because the show must go on. OK, so what are we going to talk about? So first, we'll do kind of an introduction to this problem of persuasion modeling, in particular by contrasting it with something that's probably a lot more familiar, which is response modeling. And then we'll spend a little time talking about nomenclature. So this technique is used in a bunch of different academic fields, and they all have kind of different names for it, which can make it a little bit confusing. Then Bill's going to take over and dive a little bit more into a couple of actual methods so you can understand kind of the nuts and bolts of the modeling methodologies. And then hit on a really key point, which is how do you evaluate this kind of modeling? How do you know if your models are garbage or not garbage? And then I'll finish at the end with some kind of real-world case studies from our work at Civis that can kind of show you how this technique is actually useful in the real world. So three case studies in particular. One, a project we did with Bravo, a case study around the presidential election this past cycle, and then another kind of TV ad promotional effectiveness study. So what is this all about? Let's kind of talk about the problem that motivates persuasion modeling. So there are a lot of different applications across many different domains that all have the same or similar form. And the idea is that we are trying to design and target some sort of intervention to maximize some outcome. So if you work in marketing, you might be trying to maximize the ROI on some particular advertising campaign or offer. Maybe you're sending out a coupon and you want to figure out who you should target that coupon towards to maximize your ROI. If you run a website or an app, you're trying to work on a checkout flow or some design of that site to maximize user engagement or click-through rate. In medicine, you're trying to maximize various metrics through your medical interventions. So you could put everyone in the country on cholesterol medication. That's probably not the best way to maximize your spend. You want to target it towards the actual people that need it. And then in a domain that's really familiar to us, politics, you're trying to maximize votes by designing the most persuasive messaging and then targeting it towards the right people. So let's start by actually talking about a way that people typically do this, which is through response modeling. So a common approach is you have your customer data sitting in a CRM somewhere. You take it out, you send it into the magical machine learning cloud, and out you get a ranked list of targets from your model. So basically, you're building a model to predict who's most likely to respond to your offer. You're ranking people based on that model, and then those are the people you're sending your offer to or showing your ad campaign to. If you're working in a customer acquisition context, you might use a similar technique, lookalike modeling. So imagine you have kind of a large population. This could be like a consumer database. It could be a giant list of cookies. It could be all of Facebook. And then you have your own customer data, and you kind of put those things together, and again, you build a model that says, which people out there on Facebook or in the country look the most like my customers, and then I rank those people, and they're the people that I kind of target my customer acquisition offer to. Very similar to response modeling. But the key question for all of this is, how do we know that we're actually adding incremental value with what we're doing? How do we know we're getting additional sales or users or votes and not just finding the people that would have been using us or supporting us anyway? How do we know that our offer is actually getting us new sales and not just finding the people that would have bought us anyway? So let's run a thought experiment to make this a little bit clearer. And so I'm going to focus now on kind of the sales marketing type example. So we have our customers, and then we have this kind of response model I was mentioning earlier that predicts how likely someone is to respond to our offer. And we're going to divide those people up into two kinds. The people that have high purchase model scores, and the people that have low purchase model scores. And then we're going to, in turn, take each one of those and divide them in two. And we're going to show an ad to some of them, and the others we're not going to do anything to. And then we're going to monitor all 4 of these groups and see, do they actually go out and purchase our product? So we're going to observe kind of the purchase rate. And so this is a thought experiment. We've actually run this experiment for several clients in the past, and you often see something that looks like this. So what you see is one thing you might expect. So the users that our model said were most likely to purchase, they do actually purchase at a higher rate. That's good. Our model's not total garbage, right? It's doing what it's supposed to do. And those with lower purchase scores are actually purchasing at a lower rate. Again, that's good. However, if you actually compare among the people with high model scores, the ones who saw the ad and the ones who did not see the ad, it looks like the ad actually has very, very little incremental effect, right? So the people that saw the ad, 3.1%. The people that didn't see the ad, 3.0%. You could run some tests. You could see if that's significant or not significant. But let's just assume it's basically washes out, right? It doesn't look like among people with the high propensity score that the ad is actually driving any incremental sales. However, if you look at the people that were not that likely to purchase us, it does actually look like the ad is having an effect. So, people who saw the ad were more than twice as likely as people who did not see the ad to actually then go out and buy our product. And so this might seem counterintuitive, right? You were going to target your offer before at the people you thought were most likely to buy, but that's actually where the ad's not really having much of an effect. It's having an effect among people that were not that likely to buy. Maybe because they didn't know about you, or because they were very price sensitive and the coupon really kind of pushed them over their price threshold. So the key question is, how do we avoid this, right? So how do we actually target our offer, our intervention at the people that are most likely to respond because of it, and not just to people that were likely to respond anyway, even without getting our ad or our intervention? And that is what this thing called persuasion modeling is all about. So it's kind of a set of techniques that can help overcome some of the shortcomings of response modeling and lookalike modeling. And what it does is it starts with a randomized controlled experiment. And we'll go through all this kind of in more detail in a second. But it starts with a randomized controlled experiment, and then from that data tries to identify the subsets of people that were most likely to respond to the treatment or the message or whatever it is that you're testing, not just the people that were most likely to respond. And if it's done well and the experiment's designed carefully, this technique can beat response modeling and lookalike modeling for driving incremental action. So not just finding the people that were likely to respond, but finding the kind of incremental responders. So now I'm going to hand it over to Bill to talk through some more of the details.
Sure. Thanks, Michelangelo. So as Michelangelo mentioned, this all hinges on running a proper RCT, or randomized controlled experiment. Also, A/B test are probably from the same family of experimentation. So similar to what he described a couple slides ago, we start with some universe. So in this case, it's just some set of customers. We randomly divide them into control group and then any number of treatment groups depending on how many ads we'd like to test. And the control group, we don't show anything to. The treatment groups, we show a particular ad or give them a promo or do something like that. And then we go on and we measure their purchase rate, or we measure their answers to survey questions, or we can go, if we're showing car ads or something like that, we can see who went in and did like a test drive, for example. So you can imagine after running this experiment, we get back some data that looks kind of like this. So from this point forward, we're just going to assume that there's just a control group and a treatment group just to make it easy. So in this case, we ran some experiment. We got back some data, looks like this. We have a column indicating whether or not this person went on to purchase, a column indicating if they saw the promotion or not, and then some demographic data and some information that we know about the person that we do not expect to be affected by the treatment. So things like age, state, income, maybe past purchases, things like that. And then just to get some notation down, we usually refer to the outcome as Y and then subscript it with the letter I to indicate the ith person in the data set. Typically, this treatment column is denoted as T. Makes sense, I suppose. By convention, 0 is the control group and 1 is the treatment group. And then our demographic data and any other stuff we care to include in the model is denoted with this fancy X. And then from this, so we've run this experiment, and right now, we're just answering the question, how good is our intervention overall? If we randomly selected people and gave them the promotion, what do we expect the incremental gain to be? And that's called the average treatment effect. And we get that by taking the average purchase rate in the control group and subtracting that from the average purchase rate in the treatment group. So we think of, since everyone was randomly assigned to one condition or the other, we expect that the only thing that explains the difference in the purchase rates between the two groups is the treatment itself. It's not because one group had more people from Ohio and another group had more rich people. We randomly assigned people to groups without knowledge of that, so the only difference between the groups is the fact that one group was treated and one group was not. So again, if the only thing we were interested in was just randomly selecting people and showing them the ad, then we would just stop here. We would have the number that we need. This would be the incremental gain in doing a national ad buy on TV or something like that. But as Michelangelo mentioned, we sometimes want to go further. If we do have some levers under our control, we can preferentially show some people a treatment or an intervention and not expose other people to the intervention. So we call that heterogeneous treatment effects, or HTE for short. So again, HTE is a population level average. The heterogeneous treatment effect, actually, so the population level average can mask a lot of things. So it's very possible, especially in the political context. Everybody has seen a political ad. Some make you feel the opposite of the intended effect. So it so happens that in that context, it's modelable, and a lot of other commercial applications that is also modelable. So that's what we're really after with trying to figure out if there is a differential in responses between groups or among groups of the population of interest. So I guess a little more fancy notation just to kind of set the stage. So since we can't put people, we can't put a person both in treatment and control. We have to put them in one group or the other. We can't run the same experiment twice with the same exact people because they'll remember seeing the ad or they'll remember not seeing the ad and we won't get a clean measurement. So we use this fancy notation that looks kind of weird at first. I thought Michelangelo was crazy when he was explaining this to me a while back. So again, our outcome yi, and then in parentheses, we use the treatment condition to indicate which particular group this observation came from. So 0, so yi in parentheses 0 is the outcome if the ith person is in the control group, and then same thing for yi of 1 except replaced with the treatment group. And again, the important thing to remember here is that we can't observe, for each person, we don't know their response in the treatment group and the control group. We know their response in only one of the two, so the other is essentially missing. But pretend we happen to have both numbers because we're magical data scientists and everything. And if we wanted to compute the individual treatment effect, we would just take these two numbers and subtract them, just like we did to get the average treatment effect from the entire experiment. And we denote that with this fancy little tau with subscript I. And this is called the Rubin causal model, if you see this in the literature. Very popular in social science and political science and economics, econometrics. And it's most intuitive, again, to think of this as a missing data problem. So this is the same table before, but I've added one extra column. So our outcome now is spread over 2 columns instead of just one. So we have the first column, y in parentheses 1, is the outcome for the people that were in the treatment group. And y in parentheses 0, again, is the outcome for the people in the control group. And you can see for the people in the treatment group or the people who saw the promotion, we have their outcome on the left, and for people who were only in the control group, we have their outcome on the right, and we have missing values for the ones who were not in the other group. So what we're really after is filling in the blanks in this table. And that's the most intuitive way I've found so far to think about this problem. And once you see it this way, then we can apply some of our tools for machine learning, which have been incredibly successful at making predictive models. And this particular problem is a combination of prediction and inference. So I guess another note on terminology, as Michelangelo mentioned, this goes by many names in different fields. We're calling it persuasion modeling because a lot of the techniques we're talking about today came out of our work in politics. But it's also called heterogeneous treatment effects in economics and social science. heterogeneous causal effects, also in economics and social science. And then uplift modeling or net lift modeling is what it typically goes by in the marketing literature. So again, this is a combination of techniques from various fields, and this is traditionally machine learning has kind of been isolated from a lot of other fields that are working on some of the same techniques and same problems, and this is an example of cross-fertilization between fields and a weird combination of stats and machine learning. So I guess onto a couple methods. We'll talk about two simple ones, or one simple one, one complex one. So we might start with just a linear model. So again, going over what all the letters mean. Again, we're using T for the treatment indicator, Y for the outcome. We have some other stuff that we measured about the people participating in the experiments, so x1 to xn. And then we'll break this model down a little bit. So first we have the main effects. So these are parameters that are shared essentially by the entire population. So if we were only interested in figuring out what the average treatment effect is, we just wanted the one number for how good this particular ad is over randomly selected people, we would, again, just stop here. So this would give us the average treatment effect, which would be the parameter associated with the letter T, controlling for or adjusting for the other covariates. So this essentially gets us our base rate or the average purchase rate. But what we're really after is the other side, so these interaction terms. So what we really want is the interaction of treatment and age, or treatment and state, or treatment and income. And this really gets us at the individual deviations from the average. And then I guess the next question is, say we fit this model, how do we actually use it? We just run it twice and we get the two numbers we want. To make a new prediction or to predict how someone will be impacted by being treated, we can make a prediction with the model by setting T equal to 0 and then leaving our covariates at whatever values they should take for this particular person we're interested in making an observation for, or a prediction for, sorry. And then we do the same thing, but with treatment equal to 1. And that gives us, again, from that previous table, our two missing numbers. And we subtract the 2, and we arrive at a predicted treatment effect for a person by using this fancy machine learning model that we applied to an inference problem. So on the much more complex and newer and fancier side, it's an adaptation of the CART algorithm, which is one of the canonical ways to build decision trees. This comes from a paper by Susan Athey and Guido Imbens. And the idea is we follow the normal tree building rules, but we modify the split rule. So what we're really looking for are splits that maximize the overall square of the predicted treatment effect. So we're looking for splits such that the two groups are maximally different in their response to the treatment. And again, because we've randomly assigned people to treatment and control, we can just look in each leaf node and we can actually compute the local treatment effect, which again is denoted on this particular leaf node here. So this leaf node, so I guess this would be people who have an income of less than 50K and are male. The yellow ones are the treatment group, the blue ones are the control group, and then inside this leaf node, so all the examples that share those values, in that particular leaf node, we can compute the local treatment effect, and then we can do the same thing in the other leaf nodes, and then come prediction time, we throw our new examples down the tree, see where they fall, and assign whatever the local treatment effect happens to be in that node from the actual observations. So that's well and great, but how do we know that we're doing the right thing? How do we know that this model is useful and we're not producing noise? A lot of us do machine learning, and we like one number to just plug into an optimization routine and be done with it. Unfortunately, we're not quite there yet with persuasion modeling, but there are a few simple QC things we like to do. One is just seeing how the predictions rank order with the actual observations. So this is one of the first QC plots we start to look at. So we form since we have actual observations of both treatment and control people, again, we can compute within each group the ATE, and we can see how that stacks up with our predictions. So this would be a good model. You can see that for the most part, when the predicted treatment effect is high, the actual observed treatment effect is also high. And I guess it's also important to note that just like in machine learning, you don't want to assert the goodness of your model based on in-sample statistics and metrics. So you always want to do this with a separate holdout set or by cross-validation. Another plot, which is sort of similar to this one, is called the uplift curve, which comes from marketing. So in this case, I guess this sort of gets close at, you can kind of imagine that, like we've essentially plotted the ROI of the model. So this sort of answers the what if question. So what if we targeted the top 25% of our population based on the predicted treatment effect, and if you read vertically up, you would see that our uplift in that case would be 4% using the model, and I guess let's call it 2% using the just randomly targeting, which is the yellow line. And that also gets us to statements like you can get 100% of the gain by only targeting 50% of the population. So in this case, we can achieve the maximal gain of 6.5% by only targeting 50% of the population versus 25% if we just randomly selected people. So again, this would be a good model. A bad model, we would probably see that blue line hugging the yellow line, or we may even see it below the yellow line, meaning we may have a harmful, either the model really screwed up, somebody miscoded the outcome, or what we think is supposed to be beneficial is actually harmful. So we can also get, we can compute the area of this curve, which is called the Kinney coefficient in the marketing literature, which is analogous to the ROC curve, or the area under the ROC curve in classification models. So it is a single metric that we can look at, and we can rank order models fit for a single task on this, but it's not, the scale actually matters. So there is no one number here that means the model in absolute terms is good. So it's all relative for a particular task. And we can also compare models by plotting the uplift curve for all of them. So I think this was synthetic data, but you can see some models have different performance characteristics. And with that, I will turn it back over to Michelangelo to talk about persuasion modeling at Civis.
All right, so I'm going to kind of walk through a handful of case studies to hopefully make this a little bit more concrete. But before I do that, let me just tell you a tiny bit about Civis as a company to give you context that hopefully will help make a little bit of sense. So as a company, Civis traces its origins back to the 2012 Obama re-election campaign, where a chunk of our staff was employed in kind of the analytics operation. So political scientists, social scientists, data scientists, computer folks, survey researchers, kind of all getting together to do things like field experiments, individual level predictive modeling and targeting, media optimization, and basically figuring out how to optimize all the resources the campaign was spending, targeting voters through paid media, direct mail, social media, all that sort of stuff. And since then, we've been kind of taking a lot of the similar techniques and applying them still to work in the political sphere, the nonprofit sphere, but increasingly to kind of media, customer acquisition, marketing analytics, corporate work just generally. And I think because of this interesting heritage of the company, we employ people with a lot of different backgrounds, which I think is why we've kind of been gravitated so much towards this technique that we've been talking about. So this is sort of the Drew Conway's old school data science Venn diagram. And I think the sweet spot of the company is that we've kind of grafted on this new circle onto the data science Venn diagram, which is the social science methodology part of the diagram. And we really sit in the middle of those four spheres. So people with math and stats knowledge, people who can write code, hack through data, domain expertise in a handful of these different verticals that we're talking about, but then really also the social science expertise to help design and run randomized controlled experiments and then build the modeling that we've been talking about off of those experiments. So let's run through some of the actual case studies. So the first was a project we did with the Bravo network. So Bravo was really interested in trying to attract more, they were calling them swing viewers, so more casual swing viewers to a particular show that they were premiering. So they kind of had their hardcore dedicated viewers, but they were interested in sort of expanding beyond that kind of hardcore hardcore set of viewers. And they wanted to know what messaging was going to help them do that most effectively. So we ran a large experiment for them around this series that they were premiering called Opera Ski. I don't know if any of you have actually seen it. I'm not sure I've seen it myself. It's a reality show about a ski resort and the staff of a ski resort. It's sort of like, if any of you have ever seen Party Down about catering, I think it's a little bit like that, but for ski resorts. And they had sort of these different promotional themes that they kind of had hypothesized, had this gut feeling would work towards attracting casual viewers. So one was kind of a humor-based, lighthearted thing. One was very much centered around this idea of luxury, because it was a high-end ski resort. There were kind of character-focused promos, and they wanted to know which of these were actually attractive to these more casual viewers. And so we ran an experiment like the experiment that Bill walked through. We built one of these persuasion models, and then we kind of helped them see this two-dimensional view of their viewers. So we assigned 2 scores to everybody. So the score on the left was basically kind of the equivalent of the response model. So it was a Bravo affinity score, how much you liked Bravo to begin with. So people on the right, high scores, kind of that core, I love Bravo, I watch a lot of Bravo. People in the middle, not so much. And then on the right, this is one of these persuasion scores for how people actually responded to the creative that they were shown. So in blue, these were people that had a positive effect. The promo made them respond that they were actually more likely to want to watch the show. And then the people on the left in that kind of orange spot actually had a backlash effect. And we see this really frequently. It's pretty common, especially in political advertising, that an ad or a promotion that was like really lovingly handcrafted and designed to have some intended effect actually has the opposite effect. So seeing the commercial made people even more turned off to wanting to watch Bravo in this reality series. And so then we made this two-dimensional plot for them. Each dot's a person. These are the 2 scores that I was talking about in the previous slide. And we could say things like, okay, these folks, they're likely to watch this show anyway, because they have a very, very high Bravo affinity score. These people aren't going to watch no matter what you do, right? They're very unlikely to like Bravo, and the ad that you show them to try to convince them to watch Bravo makes them hate you even more. So you should probably not target them for your intervention. But then you have this sort of sweet spot over in this part of the two-dimensional plane, which was sort of the Bravo swing viewer. So they're sort of on the fence about how much they like Bravo or don't like Bravo, but they're open and seem to be persuadable that when they see these commercials, it does actually seem to kind of make them more likely to want to watch Bravo. So this was sort of this casual group of 22 million adults that we could say to them, hey, these are the people you should actually be targeting your promotion towards, because they seem to be both kind of sort of interested in the network and also really responsive to the treatment. Okay, so I'm going to shift gears and talk about a political example next that came out of this past election cycle. So in early 2016, so I guess a little more than exactly a year ago, we did a really large randomized controlled message test for a client. So tens of thousands of respondents spread across 14 states around the country. And we tested kind of 3 broad message themes for them. One was centered around women's health. One was centered around the future of Medicaid and Social Security. And another one was kind of centered, message theme was centered around tax cuts for the wealthy. And so we went through this whole machinery of doing this large randomized controlled experiment, building persuasion models, and then kind of averaged a handful of the models that came out of it to build sort of a general economy persuasion score. So people we thought were responsive to messages about the economy, and then sort of a generic score. These were kind of people that seemed to be responsive to political messaging generally. And this is now a fairly common thing in political analytics, building these sorts of persuasion models. What we did next, which I think was really cool, was something a little bit new and I guess extended from what's typically done. 8 months later in August, kind of when the campaign was really in the thick of it, for another client, we conducted another follow-up randomized controlled experiment. So a different mode. So the previous thing was kind of a phone message experiment. The second test was a video experiment conducted only in one state, in Pennsylvania. But it allowed us to then validate the model that we had constructed before to see if, hey, this model we made a year ago, it said these people were particularly persuadable. When we ran a follow-up experiment, were they the ones who actually seemed like they were changing their opinions? And what we saw, we thought was pretty remarkable, that actually the model was doing a really, really good job of picking out people whose opinions did indeed move. So if you look at these graphs, each column represents one of those kind of persuadable universes I was mentioning. So the left column is kind of people who are generally persuadable by political messaging. Middle column, people who are persuadable by messages about the economy. And on the right, people who are persuadable about messaging on women's health. And then the rows represent quartiles of that model score. So the top row is people the top 25% of people the model said were most persuadable, people whose opinions should be shifted the most by the intervention. And then ranked going down to the bottom, people whose opinions were really, really fixed and didn't seem like they were moving at all according to the model. And then what's plotted is how much they moved in that follow-up experiment 8 months later. And you can see that it's actually, it rank orders very, very well. So people that were predicted to be most kind of malleable or persuadable actually did move the most in this follow-up experiment. Sometimes by effects that were like three or four times as large as the people that were least persuadable. And so a typical thing one might do is do this kind of shotgun approach of showing your ad or your intervention to everybody. But what we were able to advise our clients to do is to sort of target more fine-grained and target their interventions and their ads at the people that were most likely to actually have their opinions changed by them. And that results, again, in huge kind of ROI increases when you're actually targeting narrowly instead of more broadly. And finally, the last case study, again, is one around TV ad promotions, but it's a little bit different in that it has to do with observational data. So you can't always design a really nice randomized controlled experiment. We always try to convince our clients to do it, but sometimes they don't want to pay for it. So sometimes you have to just go to battle with the data that you have. And sometimes that data is observational. So in this case, the client was showing, sort of like the Bravo example, they were showing ads for a particular TV series, and they wanted to know, like, hey, is this ad actually convincing someone to tune in to the premiere of this series or not? And so we had observational data on who saw the ad, and we had observational data on who watched the series, but we didn't actually know, we didn't do a randomized control experiment. And so what you can do is take techniques from the kind of causal inference literature, techniques like propensity score matching, to kind of do an after-the-fact correction. And just really schematically, this is sort of what it looks like. You have your group of people that saw your ad, that's your treatment group, and then you have a bunch of people that didn't see your ad. And it's possible that those people are just different than the people that saw your ad, and that's not what you want. In a randomized control experiment, you want to have like the same people, and the only difference is that one saw the ad and one didn't. But so what you can do is you can build what's called a propensity model. So model who's likely to have seen the ad or not seen the ad. And then you can use that model to basically discard people who didn't see the ad, who are too different from the ones that did see the ad. So the idea is that you're kind of constructing this synthetic control group. These were like people who look like people who saw the ad, but for whatever reason, they just didn't tune in that night, or they turned their TV off. And so you start with this distribution on the left. This was the distribution of propensity scores. And after doing this technique, you get these two distributions to match. So you make basically a synthetic control group that looks a lot like your treatment group. And then you can start running all the same persuasion modeling techniques that we've talked about. And now I'm going to show kind of a handful of validation plots for a few different series. So the first series they were interested in was this kind of true crime reality series. And we built this persuasion model for them, and this shows kind of some of the validation metrics that Bill went through. So on the left, this kind of treatment effect decile plot where in orange or yellow, it has sort of the predicted treatment effect for kind of the 10% of people that are most persuadable, the next 10% kind of on down. And then in blue, the out-of-sample actual treatment effects for those people. And you can see, again, that it's rank ordering very, very well, and the people the model says should be most persuadable. Out-of-sample actually are more persuadable. And on the right, you have kind of the uplift curve. And then you can kind of go a step further and actually like look within this decile and look at some of the average characteristics of those people and sort of interpret the model for the client and tell them who is actually kind of responding most to your ad or your promotion, and give them some kind of more intelligence that they like to hear. So in this case, it was kind of older women who really responded well to this true crime series. Similar story for, it was a family-based reality series that they were trying to promote. But here, the story was even more dramatic. So basically, almost no one responded to this ad except for like the top 10% of people. There was like one very, very small, well-defined subgroup of people that responded to this ad, that top 10%, and everyone else really had more or less no effect. And in this case, they happened to be middle-aged African Americans who lived in the Southwest. Not a cat person, just happened to be one of the covariates that we had in the file for them to look at. And then interestingly, none of these commercials really seem to work very well with young people at all. So this plot shows kind of density histogram plots of age broken out by quartiles of persuasion model scores. So the green, most persuadable, down to the yellow, least persuadable. So there are very, very strong age effects showing that, like, if your goal was to convince young people to watch these programs, you're going to have to find some other way to do it because this creative is really not effective with that particular demographic. So just a few parting thoughts, and then actually it looks like we should have about 5 minutes for questions. That's perfect. So persuasion modeling, a super useful technique if you're thinking about how to optimally allocate treatments or interventions. Don't just target them at the people you think are most likely to like you or be wanting to buy your product in the first place. Think about doing a randomized controlled experiment and using some of these modeling techniques. And we've been open sourcing a handful of our data science tools in the past. And stay tuned, watch GitHub, watch our website. In the future, not too distant future, we'll probably open source a handful of our packages for doing some of this persuasion modeling. So great, that's it. Thanks, and we're happy to stick around and answer some questions.
On time.
Derek.
So you showed a few examples of these decile plots with the predicted treatment effect and the actual treatment effect together. And I think in all the cases that you showed, the top decile, the predicted treatment effect was higher than the actual treatment effect.
Yep.
For all their decile, this is lower. Is that always the case? Is there a reason?
I don't actually. So there's a broad. Oh, okay. So the question was about kind of these decile plots and comparing the predictions to the actual ones, and looking like in the top decile it over predicts, and then some of the other ones it doesn't. So I guess as a broad comment, the question of like how well they match up is sort of like it's like calibration in like a normal supervised learning model, and calibration in these models I think is like an even harder second order effect. So like we usually would not advise someone to look at the absolute effects, but to just think about the rank ordering. And I don't know, your particular question about like whether there's a difference between the top decile and the other ones, I don't know if I have a good answer. I've never noticed that or thought about it. Do you?
No, I think Derek's much sharper than we are.
Yeah, I don't know. We'll have to think about it.
So one of the problems that we faced in moving from response-based modeling to object modeling, and we had propensity modeling in the pipeline, was that it was hard to convince people. So in the case of response modeling, you have a data set where you know the responses and you model predict something, and you can directly compare, okay, this is what my model says and this is what actually happened. But here's in the counterfactual, so absent, for the same person, we really don't have a data set. So as statisticians, we understand that the value is here, but how do you convince your client that it's time to move away from response modeling and move to their subject modeling?
Yeah, so the question was like, without having labels like in supervised learning, how do you convince clients that this is a good thing or not a good thing to do? I mean, I think that's kind of the genesis of why we came up with this plot on the left, because this really is kind of the closest analog we can think of to that. Because the blue bar, you really are comparing something you know to a prediction. Because in the blue bar, it's an average treatment effect, and you know who is in the treatment group and who is in the control group, and you're calculating that treatment effect just ranked by the model score. So it really is a real thing.
So we didn't have a control group also. So we had to show that plot after like making adjustments for propensity modeling, which they themselves weren't sure about. So it was like 2 levels of.
Yeah, I mean, it is a fair point that these things can sometimes be harder to explain to clients and convince them of it. So. Cool. Any other questions?
aggregate level. But then you're trying to look at these group-based effects, which you got to randomize at the group level. So does that cause problems?
Do you want to?
No, go ahead.
So the question was, so you're looking for subgroup effects, but you haven't always randomized at the subgroup level. So I think that can be a concern, and you have to be careful when you do randomization and try to kind of block and randomize for a lot of things that you think are potentially important beforehand. So important things like race or gender or income or things that you kind of know beforehand are going to be important things that a client might want to look at. You want to be extra careful with those things when you do the randomization, and not just, you want to make sure that you're randomized across those particular things as well, rather than just flipping a coin and putting people left and right. But that is generally another fair point, that designing the randomization isn't always as simple as flipping a coin. You have to be careful when you're doing the more subgroup analysis.